Hi everybody. So in this video, we're going to look at the sum of independent probability generating functions. So we'll work through this example and then we'll try two exam style questions. And if you want to work along with me, you can download a copy of this PDF from my website. I'll leave a link below. So in this question, we've got two spinners, spinner A and spinner B, with random variables x and y. And we're told that z represents the discrete random variable, the sum of the two spinners, such that z is equal to x plus y. We've been asked to show that the probability generating function for z is the product for functions x and y. Okay, so the way we'll go about this, we'll create the generating function for z using a sample space diagram and a distribution table, and we'll compare that generating function for generating functions of x multiplied by y. Okay, and they should be the same. So if we begin by creating the sample space diagram for spinner A and spinner B, we've got spinner A with the outcomes 1 and 2, and spinner B with the outcomes 3 and 4. So if we were to add these together, we can get a 1 on A and a 3 on B. So we'll get the sum of 4, and then 5, 5, and 6. So we need to work out each of these probabilities now. So a probability of getting a 4, well, this would be a 1 followed by a 3. My probability of getting a 1 on spinner A is 1/3, and a 3 on spinner B is 1/2. So this will be 1/6. Probability of getting a 5. Well, this would be a 1 followed by a 4, or a 2 followed by a 3. So we've got 1/3 times 1/2. This will give us 1/6. And then we've got 2/3 times 1/2. So this will be a third. And adding these together, we get 1/2. And then the probability of getting a 6 would be a 2 followed by a 4. So this will be 2/3 multiplied by a half. So this would be 1/3. Okay. So for our distribution table for z, we'll have the observed value being a 4 with a probability of 1/6. And then we've got a 5 with a probability of 1/2. Then a 6 with a probability of 1/3. Okay. This will give us our generating function of z, which will be 1/6 of t to the 4 plus 1/2 of t to the 5 plus 1/3 of t to the 6. So this would be the probability generating function for z. Now we can compare this to multiplying generating functions for x and y. So we'll have, for x, we'll have 1/3 of t plus 2/3 of t squared. I'm getting that from here, multiplied by, using the distribution table for y, 1/2 of t cubed plus 1/2 of t to the 4. So now we'll expand these out. We'll have a third t times a half t cubed, so 1/6 of t to the 4. Then we'll have a third t times a half t to the 4, 1/6 t to the 5. We'll multiply these out, and we get 1/3 of t to the 5. And then the final pair, and we'll get 1/3 t to the 6. And we can collect these two together. So we'll have 1/6 of t to the 4 plus 1/2 of t to the 5 plus 1/3 of t to the 6. And this is the generating function of z in terms of t. Okay, and you can see this is exactly what we've got from our distribution table. So what this tells you is if x and y are two independent random variables, then the sum of them functions, in this case z, can be found as a product of a generating function of x multiplied by a generating function of y, okay? And we'll be using this idea as we progress through this video. So if we try an exam style question, so in this example, we're given that x and y are both distributed with a Poisson model. X has lambda 2 and y has an average of 3. We've been asked to use the standard formulae, which I've given here, to find the probability generating functions of x and y. And then for part B, given that x and y are independent, write down a probability generating function of z. Okay? So perhaps you want to try this question yourself. You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So for part A, we're told that lambda is 2, so we can substitute that into our generating function for a Poisson model. So we'll have the generating function of x in terms of t will be e to the 2 times t minus 1. And then the generating function for y will be e to the 3 times t minus 1. Okay? And then because they're independent, the generating function of z in terms of t will be the generating function of x multiplied by the generating function of y. So we can substitute in each of these. We'll have e to the 2 times t minus 1 multiplied by e to the 3 times t minus 1. And then because the bases are the same, we can just add these two powers together. So we'll get e to the 5 times t to the minus 1. And this would be our generating function for z. So then you can see then that z would be distributed with a Poisson of lambda 5. And we can tell that this is correct because you could just add the 2 and the 3 together when you have independent Poisson distributions. Let's try another question. Okay, so for our third question, we're given that x and y are independent random variables, and x has this probability generating function, and y is distributed binomially with 6 trials and a probability of success 0.1. And it is given that z is the sum of x and y. We've been asked to work out the generating function for z in terms of t, and then find the probability that z equals 0. So do you want to try this question yourself? You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So we're going to use this equation to work out the generating function of y. So this will be 1 minus p, and we know if p is 0.1, plus pt, so 0.1t, to the n, which is 6. So we can tidy this up. Will be 0.9 plus 0.1 t to the 6. And then to find the generating function for z, well, this will be the product of the generating functions for x and y. So this will be 1 over 16, 1 plus t to the 4, multiplied by the 0.9 plus 0.1t to the 6. I can tidy this up a little bit. So a generating function for z in terms of t will be 1 plus t to the 4, 0.9 plus 0.1 t to the 6 all over 16. Okay? So to work out the probability of z equaling 0, well, all we need to think about is this one term multiplied by this 0.9 term, which is raised to the power of 6. Any other combination will involve a t, and when we have a t, z will be greater than or equal to 1. So for z equal to 0, we'll have the 1/16 multiplied by the 0.9 to the power of 6. And this will give us 0.0332 to 4 dp. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.